Okay, so we're going to get into actually running some tests of significance today. In the last lesson, we talked about how to set up a test of significance, how we start with our hypotheses, where the null hypothesis is the status quo, what's being claimed to happen. And the alternative is our testing hypothesis, what we're testing to see if it's happening. We also talked about what the p-value measures that we're going to find at the end. The p-value is the probability of seeing something happen this far away from the mean or more extreme if the mean or the proportion, the claim, the parameter is really true. And then we talked about how we make a decision. Low p-values are evidence against the claim. Low p-values are evidence against the null. And we talked about, well, how do we know what's low? And so we have this level alpha set, and anything below alpha is considered low and then would be significant evidence. We also talked about that you could make incorrect conclusions, and if you do, you can make type 1 or type 2 errors. And so we talked about what each would entail and how to tell for that. And then we also discussed that the probability of a type 1 error is the alpha level. So let's do a couple of just practice questions to start out with, a couple of multiple choice, and let's see how we're doing here. So experiments on learning in animals sometimes measure how long it takes mice to find their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause mice to complete the maze faster. She measures how long each of the 10 mice take with a noise as a stimulus. The appropriate hypotheses for the significance test are, okay, so first, our null hypothesis we know is always the parameter equals whatever the claim is, right? All right, so we're talking about mean, so the parameter is mu. That means I can't have x bar, so e's gone. I also know that it's always equals the parameter. So the null can never be a less than or greater than, right? So can't be x bar, it's got to be mu, and it can't be less than. So it's got to be equals. So those are my three choices. Now, what are we testing for? Well, the researcher thinks that a loud noise will cause the mice to complete the maze faster. Okay, that's our hypothesis. That's what we're trying to test. We think it will take less time, right? Isn't that what faster means? So which one shows that? Would that be this one? Less than 18 seconds? There's your answer. So a couple things to remember when you set up your hypotheses. First of all, they've always got to be terms of the true parameter. So either mu for means or p for proportions. The null is always equals. And then the alternative is your testing hypothesis. And so whatever you're testing goes there. Okay. Exercises 26 through 28 refer to the following setting. Members of the City Council want to know if a majority of city residents supports a 1% increase in the sales tax to fund road repairs. To investigate, they survey a random sample of 300 city residents and use the results to test the following hypotheses. So the null is the claim. The true proportion is 50%. And we're seeing it more than 50% because we wanted to test to see if the majority, right? A majority would be more than 50%. Okay? Let me zoom this in a little better. All right. So where P is the proportion of all city residents who support a 1% increase. So again, remember, that's the one thing that we should have had somewhere in that last one was somewhere we should have defined, which it was multiple choice, so we didn't have to have it, what that parameter actually stands for. And so in this case, this mean would have been the average time the mice take to complete the maze, right? So here, this P is the proportion of all city residents who support the 1% increase. So number 26 says a type 1 error in the context of the study occurs if, okay, type 1 error. Remember, type 1 error is when the null is true, but we get a low p-value and we reject it. We find convincing evidence for the alternative. Okay, now I write that out first because I have in my brain what a type 1 error is, but once I start talking about the context, sometimes it gets a little confusing. And so if I have written out, okay, I know what type 1 error is this, then I can maybe get it kind of pick the correct answer then. Okay, so a type 1 error is when the null, the first one's true. So type 1, the first one is true, but my test says the second one is, right? Okay, so let's see our choices here. Finds convincing evidence that a majority of residents support the tax increase, when in reality there isn't convincing evidence that a majority supports the increase. Well, that sounds like it right away, doesn't it? Okay, so we found convincing evidence of the alternative, but we shouldn't have, right? Okay, let's read the others and make sure. Finds convincing evidence that a majority of residents support the tax increase, when in reality, at most, 50% of city residents support the increase. Okay, here's my problem with B. B is saying that we're sure of the null, isn't it? Remember, we can never accept the null. We can only reject or fail to reject it. Okay, we can either have convincing evidence for the alternative or not have convincing evidence for the alternative. The alternative is our testing hypothesis. And so it should always be written in terms of that and never approve the null. So that's going to be the problem with B. C says finds convincing evidence that a majority of residents support the tax increase, when in reality more than 50% of city residents do support the increase. Well, that's not what happened there. That would not be a type 1 error. D does not find convincing evidence when reality more than 50. Nope. Okay, so none of these are, because that's saying the same thing. E does not find convincing evidence that a majority of residents support the tax increase, when reality at most 50% of city residents do support the increase. So E and C were kind of along the same lines, and B and D were. Again, this one is going to be defining what we wrote down already. The first one's what's actually happening, but we found evidence for what was being tested. So we found convincing evidence for this when we should not have. All right, number 27 says, in a sample, p hat is 158 divided by 300, or 0.527. The resulting p-value is 0.18. What's the correct interpretation of this p-value? Okay, remember, the correct interpretation of the p-value is, this is the probability of getting something this extreme or more. So what we're assuming is, we're assuming the truth is the claim. And then the claim was 0.5, right? Okay, well, we got a value out here. That p-value is this area right here. That p-value of 0.18 is telling me the probability of being at or more extreme, at or further away from the claim. So this is saying the probability of finding a sample at this point or more extreme is about 0.18 if the null is really true, if the true proportion is really 0.5. Okay, so only 18% of the city residents support the tax increase? No. Okay, this is not telling us the proportion that support. This is telling us the probability of being in this area. B, there's an 18% chance that a majority of the residents support the tax increase. No, again, we're up here in this area, not the whole 50%. All right, C, assuming that 50% of residents support the tax increase. Okay, so this is starting out correctly, right? Because that's our assumption. Our assumption is the null is true, and it looks like all three of our last choices start out that way. So assuming that 50% of the residents support the tax increase, there's a 18% probability that the sample proportion would be 0.527 or higher by chance alone. All right, let's read the next one. Assuming that more than 50% of residents support the tax increase, there is an 18% probability that the sample proportion would be 0.528 or higher by chance alone. Okay, how is this different? Well, that says more than 50, that says 50. Okay, what are we assuming? We're not assuming the alternative is true, we're assuming the null is true, right? So that's not going to work. Okay, and then the last one, assuming that 50% of residents support the tax increase, there's an 18% chance that the null hypothesis is true by chance alone. No. So C is going to be our answer, right? We're assuming the null is true. This is the probability of being at this point or more extreme. So this is the probability of just being out here in this range just by chance alone. All right, and then 28. Based on the p-value in exercise 27, which of the following would be the most appropriate conclusion? All right, remember the p-value was 0.18. Okay, remember low p-values make us reject the null, right? Is this a low p-value? Well, they don't tell us what alpha to use, so we would need an alpha level to make that decision, right? Most commonly, 0.05 would be our alpha level. Sometimes it goes up as high as 0.1, But with either of those, this p-value is higher than either one, isn't it? So since it's large, I don't have evidence here. Okay, this is definitely a large p-value. Okay, so all of them start out with because the p-value is large. Some reject the null and some fail to reject the null. What should we do? Well, a large p-value means we fail to reject the null. So I can get rid of all the ones that say reject. Okay, so now it leads me down to here. Okay, so if I fail to reject the null, then do I have convincing evidence of anything? No. If I fail to reject the null, if my p-value is large, I do not have convincing evidence of what we're testing. You're always going to write your conclusion in terms of the alternative hypothesis. Because the p-value is large, we can't reject the null. We do not have evidence for the alternative. All right? All right, let's try a couple of just free response problems before we run into what we're going to do today. All right, as a construction engineer for a city, you're responsible for ensuring that the company is providing gravel for a new road, puts as much gravel in each truckload as they claim to. It's been estimated it will take 500 truckloads of gravel to complete this road. So you plan to measure the volume of gravel in a simple random sample of 25 trucks to make sure the company isn't delivering less gravel per truckload than they claim. Each truckload is supposed to have 20 cubic meters of gravel, so you'll test the hypothesis. So the null is 20, because that's the claim, but we're afraid they're underfilling, right? Okay. Describe what a type 1 error would be in this context. Okay, remember type 1 is when the first one is true, but we reject it in favor of the alternative, right? So a type 1 error would be they are filling the truckload up to 20. The truckload at 20 meters cubed. But our test shows they're not. Our test shows they're filling less. But we have significant evidence that they are underfilling. What's the probability of making a type 1 error when performing this test? Okay, remember the probability of a type 1 error is just your alpha level. So if they told me the alpha level is 0.05, the probability that this is going to happen? 5%, 0.05. All right, describe what a type 2 error will be. Well, type 2 is when the second one is true, so they're underfilling. They are underfilling the trucks. But we do not have significant evidence to reject the null. Okay. Now, which error, type 1 or type 2, is a more serious problem for the city? So we're looking at this in terms of this city. Okay, so a type 1 error would be when they're bringing the amount of gravel we think, or they should be, but we think they're underfilling. If that's happening, we're probably demanding they bring us more, right? And so we might end up with too much at the end. A type 2 error is where they're not bringing enough, but we think they are. And that would mean we wouldn't have enough gravel at the end. So to me, a type 2 error would be worse here, just because I would probably end up with too much. Now, that might cause issues with us and the company later if they think we're trying to cheat them out of something too, right? But I think overall, the type 2 error of just thinking it's okay, but then in the end it's not, and we don't have enough, is probably going to be worse for this city. Okay? If I were looking at it in terms of the company, type 1 might be worse, because I probably would have to come out of my own pocketbook and cover some of that I really shouldn't have to. Okay. All right, one term I want to make sure that you understand before we move on, and because we're going to hear it a lot in the next little bit, is the term statistically significant. And this is something that's very important, and you hear this all the time. Like when you see studies about different things, they'll say, well, there was statistically significant evidence. Statistically significance is just a way of saying that chance alone would rarely produce so extreme a result. Okay? When I have this distribution and I have this claim sitting right here, maybe it's a mean or it's a proportion, and then I get this sample way out here. If my p-value is really small, that means the chance of this occurring just by chance alone, the probability of this occurring just by chance alone is really, 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 really tiny. Well, when it's really, really, really tiny, that's statistically significant. Statistically significant means it's far enough away from the claim that I really shouldn't see this happen. Okay? So statistically significant tells us that chance alone, just chance variability. Remember, we talked about different samples produce different results. I expect that every time I take a sample, I might end up somewhere else in the sampling distribution, right? And that's okay. There should be some variability. But when I get way out here in the extremes, those I really shouldn't be seeing very often. And those are deemed statistically significant. Okay, we are getting ready to actually run a test of significance. Now, I was taught this way back in the day. I was taught that these are the steps you go through, and I've kind of held on to this a little bit as I taught. Your book or the Canvas modules and things called a 4-step process, so I guess I've kind of added in an extra step. But if you remember this acronym, CATCH, but spelled backwards, the word CATCH spelled backwards, this will help you remember what you need to go through. So first thing you're going to do is state the hypotheses, and we've already been practicing this. So you're going to state what the null and the alternative are, making sure that you're always using the true parameters. Remember, the null is always equal to, and then the alternative is what you're testing, so either greater than, less than, or not equal to. Also, whatever parameters you use here, whether it's mu or p, make sure you define those. All right, after you've set your hypotheses, you're going to check the conditions. These conditions have not changed from Chapter 8. All the conditions that you checked for proportions in Chapter 8, when you were running a confidence interval for proportions, those are the same conditions you're going to check here. All the conditions that you checked when you ran a confidence interval with means, those are the same conditions you're going to check here if it's a test of significance with means. Okay? The conditions do not change. All right, then you're ready to actually find your test statistic, and we'll talk about how you calculate that. And that test statistic is going to be your either the number of standard deviations you are away from the mean. So it's either going to be z or t, depending on if it's proportions or means. And then from that, you find your p-value. And then we compare our alpha to our p-value to make a decision. Remember, the alpha is our cutoff level. And if our p-value is below the cutoff level, then we're going to decide to reject the null in favor of the alternative. And then we're going to write our conclusion in context. Okay, so these are the steps we're going to go through. Okay, so if we're going to today focus on proportions. And so let me go through each of those steps individually, and then we're going to put it all together. I skipped over the hypotheses, so let me write that up here. Okay, so your hypotheses for proportions. The null is always going to be your true proportion equals some number. And then your alternative is the true proportion is either less than, greater than, less than, or not equal to, so that just depends on the context of the problem and what you're testing, that same number. So both of these should be the same symbol. If it's proportions, they're both going to be p. Both of these should be the same number. Also, you need to define what that proportion p is representing. Okay? Then you're ready to check your conditions. Okay, same conditions we've been doing. It's got to be an SRS. We got to make sure that if it is an SRS, then we check the 10% condition. Now, are there going to be times when it's not an SRS? In test of significance? Yeah. Because sometimes we are going to have an experiment. And remember, back in Chapter 4, a lot of times we can't do experiments with samples, right? We can't demand that people take these treatments. So here's what's going to happen. You're either going to have a simple random sample, or it's going to be an experiment with volunteers, but it's a nice randomized experiment. Now, you only check the 10% condition if it's a simple random sample. You only check the 10% condition if it's a simple random sample. I want to make sure that the population is at least 10 times the sample size, or the sample is no more than 1/10 of the population, however you want to look at it. But that only needs to be checked if it's a simple random sample, because I am concerned when I take people from a population without replacing them. If I haven't taken anyone from the population, like if it's a random experiment but with volunteers, there is no need for me to check the 10% condition. So make sure you have that 10% condition tied to simple random sample. When you're looking at the problem, if it's an experiment and not a simple random sample, just make sure it was a randomized experiment. People were randomly allocated to the treatments. If it's a simple random sample, then we're going to make sure that the 10% condition holds. And then we want to check large counts. Now notice, see how it's got that little p naught? This is the assumed p. In fact, here, let me rewrite my hypotheses up here. P naught is the number that we're assuming is the truth. Okay, that's what they use to assume the truth. So you're using this assumed truth to check the conditions here. Okay? All right, so hypotheses state what the true parameter is, or whatever it's being claimed to be. Check your conditions. And then we're ready to run the actual test. Now, on your formula sheet, this is what your formula sheet says as far as your test statistic. And you can find this down here at the bottom, right above confidence interval. Your standardized test statistic is your statistic minus the parameter divided by the standard error. Okay? So we can put this together if we know the symbols that go with each. Our test statistic is either going to be Z or T. And remember from the last chapter, I told you use ZapTax to help you out. If it's proportions, you're definitely using Z. If it's means, as long as you don't know the population standard deviation, which we hardly ever do, you're using T. Okay? So in this case today, we're going to look at proportions. So our test statistic is Z. Statistic, if I'm dealing with proportions, statistic is P hat. If I'm dealing with proportions, the parameter is the true P. And then the standard deviation of the statistic. Notice it says the standard deviation here, or actually the standard error of the statistic is what it says. But what we're going to do is we're going to use square root of, but we're going to use P naught. What's being assumed, let me find that last paper. What's being assumed to be the truth. Okay, whatever you put here, this number here, the claim, that's what we're using here. And technically, all three of these are going to be the same number. They just designate these as P naught because they're just showing that that's going in there as an estimation. Okay, so statistic minus parameter over your standard deviation. And here, there it is again. Now, if your alternative is a greater than whatever the claim is, you are looking for the right tail. You're looking for the area under the curve to the right of the z-score you get. So once you solve this out, if your alternative hypothesis is you are testing that it's greater than that amount, you're looking for the area above that form, that z-score. If your alternative is less than that amount, so if you've written it out and your alternative is you're testing less than that amount, then you're looking for less than whatever that z-score is. And if your alternative is a not equal to, we call this a two-tailed test because we need to find both these areas. Now, the good thing is these are equal, so you just need to find one of them and double it. Okay? Remember, when you're finding that p-value is the probability of being at that point or more extreme. So if it's above, we're at that point or higher. If it's below, it's at that point or lower. If your alternative is a not equal to, we got to find both areas, both the positive z and above and the negative z and below. Okay? And then finally, we finish this out with a conclusion and context. And much like with the confidence interval, I have kind of a little statement here, a template that you can use that you can kind of plug into every time. So what you're going to want to do is you always want to compare your p-value to your alpha level. So you're going to say, okay, since the p-value is either less than or greater than alpha, If it's less than alpha, that means there is convincing or significant evidence of whatever your alternative is. If the p-value is greater than alpha, then there is not convincing evidence of whatever your alternative is in words. Okay, so it might be worth it to have this written down somewhere to start referencing it. If you want to pause the video and get it written down, you can. But this is going to be something we're going to use over and over and over again, and it'll get in your brain just like how to interpret the confidence interval did in the last chapter. Okay. Okay, these pages are sticking together. All right, let's go ahead. We're going to run a significance test on something we started in the last section. And it says, recall our basketball player who claimed to be an 80% free throw shooter. In a simple random sample of 50 free throws, he made 32. His sample proportion of made shots, 32 out of 50, which is 0.64, is much lower than what he claimed. But does it provide convincing evidence against his claim? To find out, we must perform a significance test of, so our null, the proportion is equal to the claim, and we're testing to see if that true proportion is actually less than what's being claimed. Notice that the p used here, the parameter used here, has been defined as the actual proportion of free throws the shooter makes in the long run. So we're starting out with our